Efacec is the largest Portuguese company in the electromechanical industry sector. The Efacec Energy business unit provides a broad range of products and systems for the global energy market. As a 5-growth industrial partner, Efacec Energy is committed with one pilot in the energy vertical, one of the 4 vertical pilots of the 5-growth project. The energy vertical pilot is deployed inside the perimeter of the University of Aveiro, and explores the capability and enhancements of the 5G technology, provided by the 5-growth platform in integration with the 5G VINI infrastructure and services, to enable advanced management solutions for the energy market in the low-voltage distribution segment. The energy pilot unfolds in 2 different use cases. The first use case aims the advanced monitoring and maintenance support for the secondary MVLV distribution substation. This use case is enabled by 5G connectivity in the secondary substation side, to a 5G standalone network providing low end-to-end latency and high throughput in the communication between the geographically dispersed secondary substations and the utility control center. The second use case aims the advanced critical signal and data exchange across wide smart metering and measurement infrastructures. This use case is enabled by 5G connectivity of the low-voltage automation devices to the 5G standalone network, providing high availability and low end-to-end latency in the communications between the low-voltage sensors dispersed across the LV distribution network and the low-voltage controller placed inside the secondary substation. The first use case is already partially deployed in the 5-growth platform and will be detailed here. As mentioned before, it aims to enable advanced remote real-time management of the secondary substation. This means that the control center operator will be able to get real-time information concerning a fault occurring inside the secondary substation, including live telemetry of the electrical equipment and video streaming from the substation interior, this way optimizing the utility operation reaction time, and supporting a more accurate maintenance planning and a more efficient evaluation of the human and physical needs to resolve the fault and restore the power supply, therefore reducing the utility OPEX. By month 18, the first use case, including all the secondary substation automation, is deployed in laboratory environment inside IT Aveiro building. The 5G connectivity on substation side is achieved through a Huawei 5G CPE Pro 2, connected to the Altis Labs 5G standalone network. One ASOX radio unit deployed inside the lab is wired connected to the ASOX CU and DU, and the Open 5G core solution deployed in the Altis Lab, also inside the IT Aveiro premises. The 5G core is connected to the IT Aveiro data center network, this way establishing end-to-end connectivity between the substation automation and the control center SCADA ADMS system. The Efacec Energy pilot use a physical 5G infrastructure integrated by Altis Labs, comprehending the Open 5G core developed by Fraunhofer Focus, and the ASOX 5G standalone radio access network. The standalone RAN is based on a Cloud RAN architecture, CU plus DU and RU. The ASOX RU is TDD-based, using a maximum bandwidth of 100 MHz in the 3300 to 3800 MHz band. The Cloud RAN architecture facilitates and decreases the capex of the network deployment, and it is a mandatory technological solution for the network densification. The Open 5G core is located in IT Building 1, and the standalone RAN in IT Building 2. During November of 2020, interoperability and performance tests were carried out and some issues were identified and solved, which means that the 5G network and vertical setup is ready for the next phase, bring the pilot into its real environment. Concerning the secondary substation equipment, we have the Efacec G Smart as the low voltage controller, and the Efacec LVS3 as the low voltage sensor. The G Smart is responsible for collecting electrical measurements directly from the low voltage end of the power transformer, and for receiving the measurements and signals collected by the low voltage sensors. The G Smart is also capable of collecting signals from the substation, such as the intrusion detection and the working status of the IPHD camera. The LVS3 is mounted in the low-voltage outgoing feeders of the secondary substation, and besides collecting electrical measurements, it can collect signals from the feeder equipment, like a blown fuse. We have also the intrusion detector, the IP surveillance camera and the 5G CPE that provides radio connectivity to the 5G standalone network. The image on the left shows the Energy Pilot bench inside the IT lab, holding all the equipment belonging to the first use case. This equipment will be moved to its final destination at the secondary LVMV distribution substation at the end of February. On the top right corner we have a detail on the control center operator interface. The IT data center, where the control center software is hosted in a virtualized environment, is depicted in the bottom right corner. The depicted diagram reveals the data flows and the measurement locations concerning the first use case. The majority of the network packages will flow uplink. This use case will exercise two main application areas for the enhanced capabilities of 5G, the ultra-reliable low-latency communications, and the enhanced mobile broadband. This demonstration showcases the first use case of Energy Vertical, in particular what happens when an abnormal event takes place inside the secondary distribution substation. For that purpose we will use an intrusion detector that will be actuated by the operator to simulate a door opens in the secondary substation. The intrusion detector signal is acquired by the substation controller and immediately transmitted on a SCADA protocol, IEC 104, to the control center. We can see that as soon as the intrusion detector is triggered, a new alarm event shows up in the alarm list interface on the operator screen. Also, other interfaces like floating lists or diagrams are immediately updated with the new status. To ensure a reliable real-time operation of the network and a smooth experience for the operator, a sustained low latency on the communications network is mandatory, not exceeding 100 milliseconds. The operator will then track down the abnormal event just arrived, opening the single-line diagram of the problematic substation from the alarm list entry. The diagram exhibits a set of dynamic information concerning the secondary substation telemetry. Measurements, like current and voltage, or signals like blown-up fuse or an intrusion detector actuated, as we can see on the top of the window. That blinking door is telling the operator that something requires his immediate attention. The operator will then be able to open a video streaming transmitting from inside the substation to get further information about the root cause of the abnormal event. This can be particularly useful to the operator assessing what is going on inside the substation. Maybe a fire on the power transformer or a human or animal intrusion. He can then pass accurate information to the maintenance team on the field, saving valuable time preparing the intervention to resolve the occurrence. We can see that the throughput in the 5G connection is now considerably higher due to the video streaming being transmitted to the control center. This enhanced supervision of the secondary substation would not be possible with the communication technology currently deployed in the distribution network across the secondary substations. We are talking most commonly about GPRS, with very low throughput capabilities and higher latency than required for real-time remote operation. We can see in the operator interface that we have good quality video streaming from inside the substation. At the same time, the telemetry from the electrical network and from that substation in particular, continue to arrive to the control center in real time. The operator can accept this alarm or any other, and in the event of new abnormal occurrences in the network they will continue to arrive to the control center and show up in the operator interface. During the preliminary tests, to analyze the performance of the 5G standalone network, two tools were used: ICMP Ping, to evaluate the application end-to-end round trip time, and iPerf, to measure throughput capabilities of the network in UDP and TCP transport layer protocols. The results obtained in this campaign are summarized in the depicted figures and tables. The business needs concerning the advanced monitoring and maintenance support for the secondary distribution substation were here presented, along with the implementation and deployment within the vertical pilot. A 5G standalone infrastructure is integrated, deployed and configured in the 5 Growth pilot site at University of Aveiro, providing low latency and high data rate, supporting both real-time telemetry flow and video IP streaming requirements. End-to-end performance tests were carried out, giving good indications on latency and data rate KPIs pursuit, and enabling tuning the 5G network configuration.